Okay, so now it's already 11:05. So yeah, let's start. So this talk is about towards enabling KV cache optimizations in LMCache, and I'm Kuntai. I'm the viewer, I'm an LMCache committer, and I'm a LMCache maintainer, and also like I'm chief scientist from TensorMesh. So after this talk, so let's have a very brief like overview of this talk. So basically, uh, in the KV cache industry, the our like the current practice is that people store and transfer KV caches all over the cluster. So like from this GPU to CPU to disk and even to a remote machine or even to S3, those things are already happening. But in academia, there's a pretty promising direction where you can optimize KV caches using AI and ML techniques. So does this require new infra? It might, but with LMCache, you can have them both. And today's talk will be more focusing on this academia bit of KV cache optimizations. What is KV cache optimizations and why is it useful? And why is it beneficial to like the inference performance? Yeah, and so like at a high level, this KV cache optimizations are made of KV cache operations, where operations basically compression, quantization, token dropping, or turbo quant, anything you heard of. And KV cache orchestrations will be when to execute these operations on what KV cache. So today's talk will be focusing on KV cache operations, and we'll introduce two new APIs for people to use. The first API will be KV cache encoding decoding. The second one will be token ID-based KV cache put and get. So I will talk more about like how to use those APIs in the future slides. But more APIs are coming, and let's start. So this is like a really quick overview of the whole talk. Okay, so let's start from the beginning, and feel free to like raise your hands if you have any questions. I will answer that. I will answer them. So the quick outline is that we first talk about the potential of KV cache optimizations, and the second part will be the difficulty of implementing optimizations in inference engine, and then we talk about like how do we implement those KV caches optimizations in LMCache, and the fourth part will be a very quick show of our vision. So let's talk about the potential and the yeah. So basically, KV caches are the key to efficient LLM inference. Like, so basically, when users send out OpenAI API request, they will go through an LLM inference engine, and what backs those inference engine up is KV caches. So with KV caches in hand, we can cut GPU costs, we can reduce request latency, we can we can avoid redundant computation, and we can even use it to affect generation quality. So yeah, the key is to really build up a KV cache infrastructure to accelerate LLM inference. And the status quo of KV cache infrastructure is that existing infrastructure are storing and transferring KV caches across cluster. So this is a pretty good thing, and it's very useful. But the observation is that it's getting matured. So by matured, I mean that remaining works on this part are more on expanding support, like supporting new large language models or supporting new hardwares, including more diverse GPUs and more diverse storage hardwares, rather than optimizing for pure performance. So this is technical wise, like the performance juice on the major ecosystem path, which is basically NVIDIA GPU plus CPU plus network and plus like a basic RDMA based transfer. That path is pretty matured, and it's saturating the link bandwidth. It's a pretty good thing. But the question is that what is the next thing on KV cache infrastructure after we saturate the perf on major ecosystem path? So the opportunity where I found or we found is that inference time KV cache optimizations have high potential, but are not being widely deployed. So there are multiple keywords in this sentence. The first part will be the inference time KV cache optimizations. So the reason why doing KV cache optimization and inference time is that compared to doing it in training time, where most of the model vendors are already doing it very heavily these days. So it's because at inference time you can access more information. you can use later tokens to improve earlier tokens KV cache. This is not doable in at training stage or at model vendor stage because model needs to be autoregressive. You have to generate KV caches one by one. And when generating new KV caches, you cannot look future tokens. If you look future tokens, it's no longer able to make sure things are causal. And the second benefit is that if you do KV cache optimization at inference time, you can be much more flexible. So for example, you can encode KV caches to bytes. And this is typically not very useful in training time. But at inference time, if you encode KV cache to bytes and put it to storage, you can have a very low loading delay of KV caches. But as we all know, like loading KV caches at training time, especially at pre-training time, it's not very useful. Okay. So I see a question from
Hi, can you hear me?
Yeah.
This is a very interesting topic, and I remember you mentioned in one slide before, and the data movement or overhead is a problem because KV cache will be transferred across the cluster. Is this happen on the inference time?
This happened on the inference time. So by inference time, I broadly define this as like everything happened around inference engine. So like including KV cache unloading and offloading, not only the inference critical path.
Oh, okay. So this also include the KV cache transfer, right?
Yes.
So okay. I have a question, but I will ask later. Yeah, thank you.
Yeah, sure. Sorry. So the second key point of this sentence is that inference time KV cache optimizations have high potential. So to quantify this, let's look at this figure. And so basically this figure, I'm using the data source from NVIDIA KV Press. So it's an official project from NVIDIA. And this project is pretty selective. It is selecting some of the pretty promising KV cache optimizations published in recent literature. And so basically, to quickly illustrate the background of this figure, the x-axis is the compression ratio. The y-axis is the evaluation accuracy. The data set is on Ruler. Data set published by NVIDIA, and this model is Qwen 8B. It's a slightly old model, but it's still like a pretty good model. So let's look at this like very top upper right purple points. So this purple point achieves 4x compression with very little quality loss, at least on this data set. So this mere purple point means that we can have 4x shorter time to first token because it gets compressed by 4x and 4x KV cache loading throughput, and maybe up like more than 2x decoding throughput with ideal implementation. Of course, with ideal implementation, but yeah, so at least the potential is clear. Yeah, and yeah, feel free to ask questions. Yeah.
Yeah, sorry, it's me again. So I see one line may have different compression ratios. So may I know why is that? Do they use different algorithm on a certain data set or a certain problem?
So these different colors of lines are generated by different KV cache compression algorithm. And the green dots, I forgot what algorithm it is using. Maybe it's dual attention. So some of the attention, even if you specify compression ratio, you cannot. It's not being able to strictly stick to that compression ratio, and which cause their compression ratio to be not fully stick to, for example, 4x.
Oh, okay, okay. So do they use standard compression algorithm like Z standard or like quantization?
They use machine learning algorithms, for example, like maybe KV cache token dropping, KV cache quantization, those kind of techniques.
Oh, okay, that makes sense.
Yeah.
That you can define the error bar, the compression ratio. I mean, yeah. Thank you.
Yeah. Okay, so hopefully you now appreciate the potentials of KV cache compression and KV cache optimizations. So KV cache optimization are far beyond KV cache compression, but I think compression is a pretty good example to like as a first starting point. But given that KV cache optimization has pretty high potential, we of course want to bring them into production system. But in fact, implementing KV cache optimizations, especially in inference engine, is super difficult. So this is the third point of this sentence, where it's basically KV cache optimizations have high potential, but are not being widely deployed, and that's the current status. So the reason is that it's really difficult to do it inside Survey Engine, and the pains comes from multiple dimensions. The first dimension is, of course, you have a very huge compatibility matrix to handle in inference engine, and this is seemingly subtle because like KV cache optimizations are just optimizing KV cache, but in fact, KV cache touches almost everywhere in inference engine. So let's take this TurboQuant PR from VLM as an example. So I'm taking this as an example because it's already merged. So there's like 27 files changed on these files changed, and there's like 3K line of code. And within 1 month, there's 7 follow-up PR just to fix the bugs and to improve the performance of this of TurboQuant. So it's not very smooth experience for especially machine learning developers. The second part is that it requires functionalities that does not make sense for inference engine, and this is a strong argument. Let me show you. So let's take this paper as an example. So this paper is KVZip, and it's like one of the techniques selected by KV Press, if I remember correctly, has pretty decent performance. But the downside is that it needs to do prefill 2 times. Yeah, prefill the same prompt 2 times. And that really doesn't make too much sense for inference engine. You don't want your prefill to be slowed down by 2x. And another example is that SnackKV. So SnackKV is like it's pretty good. It's a very good baseline, and it's actually one of the most popular baseline in all the KV cache compression literature. But it partially materialized the attention metrics. So we all know that the existing like attention kernels trying all optimize. They optimize for performance with the cost of not being able to fully materialize attention metrics. So if you really want to do that, attention kernel will perform really, really slow, and that significantly drags down the inference engine performance. And even this optimization cartridge. So this is also one of the famous paper. It's a pretty recent work. The tricky part of this paper is that it needs to not only do like the inference pass, it also needs to do the back propagation pass to get the gradients. You can't expect inference engine to store all those intermediate results and deploy all those extra kernels just to get gradients for this KV cache optimization. So it's not really doable in inference engine. And another reason is that some of the KV cache optimizations, they even require cluster view. So this paper, like Impress, is a system paper. It basically does token dropping across storage tiers. And since like in inference engine, you really only have the local view of the KV caches on your node. You don't have the like cluster view to support the cross-tier cluster-wide decisions to make the best KV cache token dropping choices. And of course, it's very hard. It requires very heavy perf tuning. As a fun fact, initial VLM TurboQuant implementation decreased inference performance, even though it compresses KV cache by almost 4x. So that's a sad fact. But these KV cache optimizations are pretty slow without careful engineering. So by careful engineering, it's like you write very fancy kernels and do some like or head into Triton, and this PR is already doing that, but it's still pretty slow. So it's very hard to tune the performance for these optimizations. That's what bring our team that's what bring me to thought like LMCache might be the best place to implement those KV cache optimizations. So the key reason is that existing KV cache libraries, they collocate KV cache optimizations with the inference engine, and that naturally creates contention. So for example, you need to they need to share the GPU. So like they will try to schedule compute kernels on GPUs, and that creates contention. And also Python level, these KV cache optimizations might need to occupy GLL for a long time, and that's not a good thing for inference engine. So what we are thinking of in LMCache side is that we are putting the KV cache optimizations outside from inference engine by our LMCache multiprocess mode. So instead of directly plugging KV cache optimizations to the inference engine, like LMCache allows you to plug the KV cache optimizations outside the inference engine in a different process, or even on a different node, and this allows us to detach KV cache optimizations from the inference engine. So the benefits and limitations. Of course, this is not a perfect solution. But the benefits is clear. So with this KV cache optimization implemented outside the inference engine, you can still get a wide range of performance benefits. Time to first token, of course, because LMCache handles like KV cache loading, and KV cache loading throughput. That's also because LMCache handles KV cache loading for you, and also more importantly, this implementation can even allow you to increase decoding throughput by token dropping, by those optimizations that does not require attention kernel change. And also it's very developer friendly. You can see the APIs later, but it's very easy to program, and you have cluster-wide information in the future. Not at this API, but you can have cluster-wide view in the future. And very flexible placement. You can place it inside the inference engine, inside the inference engine node, or even on a different node. And for me, the key limitation is that we cannot use custom inference kernels to further increase decoding throughput. So for example, TurboQuant. For TurboQuant to increase decoding throughput, it needs like some custom kernels to perform like a rotate the KV cache back to the original space, and the dequantization, all in GPU. And doing those obviously requires like pretty performant GPU kernels, and that's the bit where the current infrastructure cannot touch. But still, quantization, like especially like those optimizations that changes attention kernel, those optimizations are not the only optimizations that increases decoding throughput. Token dropping can also do that, and token dropping is much easier to implement in practice because it does not change kernel. Okay, yeah. So hopefully now you know the benefits and limitations of the KV cache optimizations. Now let's dive into this API overview. So I roughly partition KV cache optimizations into two very high-level dimensions. The first dimension is KV cache operations, where basically you're transforming one KV caches at a time, and this is like compression, quantization, token dropping, those kind of operations, and it will be the focus of this talk. Another dimension, where I leave it to later working on LMCache, but we will do that, is KV cache orchestrations. So orchestration is infrastructure to determine when to execute what KV cache operation. It's a cluster level decision, and it's pretty complicated to do it right, actually. It's not very easy. So regarding the KV cache operation API, we have two API. The first API is this encoding decoding, where you can encode or decode the KV caches to bytes. So you can do quantization, and you can do you can even use some like arithmetic encoding codec to do further compression to compress them into bytes. And it's naturally plugged in with it naturally plays well with the storage with the current design, so that if you implement it in LMCache, you can automatically plug it into like all the storage backends that LMCache currently support. So that includes like Mooncake, and that includes like Nixel-based storage. So imagine all Nixel-based storage can benefit from that. And the second part will be the token ID-based KV cache put and get. So this API is a distributed API where it allows you to run a more heavier KV cache optimizations on a different node. And I will talk about more details of it, but this KV cache put and get API is also pretty easy to use. So yeah, hopefully feel free to use them. The first API, let's dive. So after this high-level introduction of this API, let's slightly dive into more detail. So the first API will be the KV cache encoding decoding API, and this API basically it transforms the LMCache's internal memory, which is called memory objects, that contains raw chunks of KV cache. It transparently transforms them into like the encoded version of these memory objects, and then the And then the underlying storage in LMCache, it is implemented in a way that they can serialize and deserialize, store and load all the memory objects. And they like this storage does not care whether this object is encoded or decoded or not. It just blindly put all the memory objects inside their storage. So with this transparent translation, you can already encode that you can just perform encoding and decoding very easily by this like serialization deserialization processor. So as a metaphor, you can think of this serialization deserialization processor as a pipe. So basically, it pipes in the raw chunks of KV cache and pipes out the encoded chunks of KV cache when stored. And upon load, it pipes the encoded KV caches, and then it pipes out the decoded raw chunks of KV cache. And of course, this encoding can be lossy depending on your preference. Yeah. So if you want like lower storage, you can make it more lossy. But if you want like better inference like results, better inference accuracy, make it less lossy, it's still beneficial. And the APIs are only 3 functions. The first function is called serialize. It serializes a source memory object to a destination memory object, and it returns number of bytes being written to this memory object. The second API is deserialize, where you basically deserialize the data from source to destination. And there's an important third API we currently have, which is the estimate serialized size. So so this returns a conservative estimation of like how much bytes you will need in order to serialize a KV cache with a certain shape. So we have this API because we want to make sure that there's much less CPU memory fragmentation in LMCache. So we need to know the KV cache size. Sorry, we need to know the number of bytes before serialization in order to make optimal memory decision, CPU memory decision. So yeah, as a fact, in the current KV cache offloading, in the current KV cache infrastructure, the CPU is not a scarce resource. It's pretty tight. So that we have this extra API to make sure that the CPU memory are being well organized and there's little fragmentation in it. Okay, so this concludes the first API. Let me know if you have any questions. So the second API will be token ID based KV cache put and get. So let's take a quick look at the workflow of this API. So basically, this API is, as the name suggests, it performs KV cache put or get using token IDs. So let's take a look at a get operation as example. So first, the KV cache organization submit the model names and token IDs, and we transfer them from LMCache SDK to the HTTP server at the inference engine side. And then this HTTP server will look up the KV caches in the format of chunk. And then it will stream those like KV caches back to LMCache SDK in a chunk format. And then LMCache SDK helps you to reorganize the KV caches into contiguous KV cache. And so that from the KV cache optimization writer side, you basically send out the model name and token ID, and you get the contiguous version of KV cache. And here's a quick example usage of how to use this API to achieve like token dropping. So basically, you first import the LMCache SDK, and you send a request to inference engine. But after sending a request to inference engine, you can limit the amount of tokens being generated. For example, maybe 1,000 token. And then you retrieve the KV cache, perform the token dropping to get the new KV cache and the drop tokens, and then use our store API to store the KV cache, and then send the request back to inference engine again. So by using this loop, you can achieve the benefit of token dropping, which is your decoding throughput can be much larger, though there's like a slight overhead of like moving KV cache, like interrupting the KV cache, interrupting the inference of one request to perform this KV cache transformation in a blocking way, though it's blocked by another node, and that introduces overheads. But in the future, this part of like KV cache transformation and token dropping can be done asynchronously with inference engine. So that's also what we are working towards. But the first version of API will be like this kind of like blocking API call, which already allows you to increase the decoding throughput by a lot at the cost of inflating the worst case, like the P99 time per output token latency. Okay, so this concludes all the technical part of this talk. And at last, I want to quickly share our vision. I'll ask you a question, but I'll answer them like very quickly afterwards. So our vision is that KV caches is actually a game changer in the industry. So the reason is that KV caches has so many functionalities and so many roles, which is pretty rare in existing computer science history. So first is the intermediate compute states, which means that you can reuse it to skip computation and reduce delay. A second is like a large language model's internal understanding of a context. So it can be approximated while fully preserving its semantics. And third is also what LLM uses to generate output. It means that you can manipulate KV cache to influence output accuracy. So we believe KV cache is not merely tensors, it's the big data for large language model era. And so we are pivoting LMCache from our original goal, which is fast community-driven solution that connects inference engine and entire storage with KV cache, to a fast, intelligent, cluster-wide community-driven KV cache service for large language model inference. And the LLM stream of an electric LMCache. And that concludes my talk. I'm happy to take any questions. So let me check the chat. Okay. Are there any specific considerations on how the error overhead between inference server and KV cache optimization server affects the end-to-end performance? So basically, let me circle back to this like a small SDK implementation. So in the current version of implementation, the KV cache token dropping in this example is done one time per 1,000 decoding steps. So it takes the inference, it takes the request out and do the transformation outside of inference engine, and then put it back to the inference engine, so that it does not reduce the GPU utilization of the inference engine, because the optimizations are all done outside of inference engine. So in terms of end-to-end metric, I would expect all the throughput metrics can be improved. So you can have higher throughput across you can have higher decoding throughput across the board. But the cost is that the delay of one request, especially during decoding, might be longer. So it's because you stop the request for a while just to perform the KV cache token dropping outside the cluster, outside the inference node, and that takes some time. So the time per output token, especially in worst case, especially the P99 and the tail, will be worse. Yeah. Are there any other questions from the audience? And let me see. I think that finishes all the questions from the chat. Feel free to ask any questions.
Let's wait 30 seconds. Some people need time to type.
Yeah, sure. Please feel free to type. Yeah.
Or you can talk directly as well, if you'd rather ask your question verbally.
What is the ultimate benefit by allowing the optimizations to happen during inference time? So for me, in terms of pure performance, especially when especially in terms of the request that is being optimized, the key benefit is that the decoding throughput can be much larger. And this is very useful for thinking models. So thinking models just naturally emits so many tokens before it generates any specific outputs. And with this framework, with this token dropping framework, the thinking process can be accelerated. Yeah, feel free to ask. Yafan, right? Yeah.
Yafan, yeah. I do have another question. I'm not an expert in KV cache, so I'm quite curious about one slide you mentioned before, which is a token ID based. Can you go back to that page?
So you mean this page?
Yeah, token. Yes, token ID based. So do you mean for each token you can find the corresponding KV cache inside? Is that doable?
Not actually. So basically, this token ID based means that the user submit a sequence of tokens, and then we LMCache responded with the KV cache corresponding to that sequence of tokens. So basically, KV caches are being determined by a sequence of tokens instead of just one single token itself.
Okay, I see.
Yeah. So even for the same token, if its pre-pending tokens are different, its KV cache will be different.
Okay, I see. So understanding the semantic between the real token, and the KV cache is still a problem, right?
Understanding the semantics of tokens and real tokens. So tokens are meant for. So basically, tokens are like another representation of KV of the data, where it's not being processed by large language models, but KV cache is like already being processed of large language models. It does not only include the original context, it also includes the model's understanding of this context. So like the model will interpret the context and understand what's the meaning inside those contexts, and embed them into KV cache.
Oh, I see. So if I have different language model, the KV cache will be totally different in like data pattern distribution, the value range, they will be totally different, right? Very specific to large language model.
So good question. Not really. So like they will be like they're of course not fully the same. That's for sure, because models are trained differently. But there are some common characteristics that are that are shared across models. So for one example is attention sync, where the first few tokens systematically has much higher attention than remaining tokens in the current large language model. That things tend to preserve across a lot of models. And the second thing is that like some of the heads of the KV cache are having much larger value than other heads. So there are some mysterious attention heads that just seems to be more important than others. So that the model learn to give it much higher value, numerical value.
Oh, I see. That's very interesting. I will check it in the future. Yeah, thank you.
Yeah, sure.
There are two more questions in the chat.
Okay. Do you see any value GPU-based compression or decompression? Yes, of course. So basically, like in the current framework, the compression, like the API 1, which is a compression decompression API, this compression happens between CPU and storage. So it means that compression is only like the compressed data will be only stored in the storage, not in the CPU. And with GPU-based compression or decompression, it can make CPU store more KV caches by reducing the size. And it can also allow the GPU to store more KV caches by reducing its size. So it can have higher hit rate, have higher KV cache hit rate compared to not having this compression. And also with GPU-based compression or decompression, you can increase the decoding throughput because you can store more KV caches in the GPU. You have a larger batch size, and the decoding throughput will be much larger. With that being said, GPU-based compression or decompression is also one of the hardest part of implementing KV cache compression algorithm. It's very performance sensitive, and you have to interleave it really well with the inference code path, else your performance will really not going to be good. And compression decompression algorithms most of them are pretty heavy. So by heavy, I mean that it's not just a trivial quantization. It basically requires like a pretty large matrix multiplication in order to compress them really well. And KV cache is large, and multiplying them in GPU is also a operation that takes a lot of time. So for GPU-based compression or decompression to be performant, it somehow needs to be simple in terms of like maybe just doing some like very quick compression, and it needs to interleave really well with the GPU architecture. So it has the highest potential theoretically, but in practice, it's also the part that has most constraints. Okay, yeah, thanks for the good question. And the last question will be like, token dropping takes into consideration short-term or long-term mixed workload. I'm not sure what short-term and long-term means, so I interpret them as like a short decoding or long decoding workload. So token dropping will be much better in long decoding workload, because it increases the decoding throughput, but it also creates overhead. So that overhead won't be worth it unless the decoding is pretty long. Yeah. The last question, as I found out, is that can you confirm how we can still reach high throughput with these optimizations while having longer time per output token? So basically, imagine a system that is, so basically that is because the overheads introduced by the token dropping is not on GPU. So the GPUs are like almost always fully utilized, and GPU like if you have and the decoding throughput is mainly depending on the GPU utilization. So if your GPU is fully utilized, the decoding throughput is high, and because every work on GPU you process on GPU are leading to a decoding token being generated. So as long as you do not let GPU sit idle, do well engineering and make sure that one request is being token dropped, there's other requests being run on the GPU, then the decoding throughput will still be high. Yeah, thanks for the great questions. If there are any other questions from the audience? Yeah, so I guess that's all for today's talk, and thank you for coming. And please feel free to use those APIs. And I guess for me, it's one of the most easiest to use API compared to compared to writing things in inference engine. It's much flexible and pretty easy to use. So feel free to try them. Yeah, thank you. So yeah, our vision is, again, we want to build a fast, intelligent, cluster-wide, community-driven KV cache service for large language model inference. And we hope that machine learning developers can also join in this effort to build a better infrastructure with us. Yeah, thanks.